All right, so number 2 on this worksheet is just a quick concept check to make sure we got the idea of how to apply this expected value. So here we have another simple game based on a die, and here there's just 3 events. The first one is you roll a 1, 2, or a 3, and in this particular game you earn 24 points. You roll a 4 or 5, you lose 15, and if you roll a 6, you lose 6 points. So the question is, if you played this game over and over and over many times, what would you expect to win or lose per roll on average? And it's not super obvious by looking at this. It certainly looks like it's going to be between 15, which is the worst outcome, and negative 15, which is the worst, and positive 24, which is the best. But we can use this expected value technique. So here we already have the events listed, we have the payoffs listed. So here we just need to write the probabilities. Well, the probability of 1, 2, or 3 is simply going to be 1/2. Probability of rolling a 4 or 5 is going to be 2 out of 6, or 1/3. And rolling a 6 is going to be a 1/6 probability. Check to add do these add up to 1? Well, yeah, 1/2 plus 1/3 is 5/6 plus 1/6. So yes, the sum equals 1, so that's good. And then the contribution expected value, just multiply across. So here we do 24 times 1/2, that's positive 12 points. Negative 15 times 1/3 is negative 5 points 1/3 of the time, or 15 points. Negative 15 1/3 of the time gives us negative 5 kind of overall. And then here we have negative 6 points times 1/6, that's minus 1. And then we just go ahead and add this column up. The sum here, which is going to equal the expected value, is simply 12 minus 5 minus 1 is 6. So it looks like if you played this game over and over and over, you would expect to earn positive 6 points on each turn with this game. The next question then says, well, what do we need to change this circled value here to in order to have the expected value of the game be 0? So right now the expected value of the game is 6, and we want it to be have an expected value of 0. When we have expected values of 0, in a game, we consider that to be a fair game, because no one's really going to win or lose. In this case, whoever is winning the 24 points is going to win over time, because they're earning 6 on average, and so we want to change that so that they break even and earn 0. Well, my guess is that it would probably be relatively easy to back into that, and for a lot of you probably see right now what the answer is, but I'm just going to go through the full algebraic technique of how to think about this. And here I'm just going to give that a variable name. X is going to be that new payoff, and so let's write the expression for the expected value. Well, instead of 24 now we have X, so we're going to have X times 1/2 plus negative 15 times 1/3 plus negative 6 times 1/6. That's the full expression for expected value, where we've just taken each payoff multiplied by the probability. Now in this case, oops, I have the eraser on here. In this case, we want to set that equal to 0. Now we just have a simple equation which we can go ahead and solve. It's going to be x over 2 minus 5 minus 1 equals 0. Keep solving up here. We have x over 2 equals 6. X equals 12. So we'd have to change this payoff here to be half as big. Positive 12 points would have it be a break-even game. And it sure makes sense that it went down, because right now this game, before we made the change, was weighted toward winning positive points, and so we would need to make that number lower in order for this thing to come down to 0. And you probably could have just seen right here that we needed this contribution to expected value to be 6, and so therefore that would have had to have been 12. So if you saw that right away, that's fine. But again, I just wanted to go through this algebraic idea of how to do it in a more generic sense. Okay, this next one is maybe a little more realistic example where we have this idea of a state lottery. Wink, wink, you might want to think about this for the project. But the idea is that in this simple lottery, there's 6 numbers that are randomly chosen without replacement from the numbers 1 through 40. So there's 2 things that are going on. You choose some numbers, and then the lottery themselves chooses 6 winning numbers. And so when after there's a win, or after the lottery folks choose their numbers, you can think that you can divide those 40 balls into 34 losers. Sorry about that. And 6 winners. And so then your job is to have picked something from the winning collection. And so that's how we're going to think about this probability. You have to kind of go back to remembering how combinations work here. And so when you, essentially what you're going to do initially is pick 6 numbers out of 40. So the probability denominators for all these guys are going to be 40C6, because that's we're just choosing 40 or 6 numbers out of 40 balls. And 40C6. So this first one here is, well, in order to win the $1 million prize, we have to correctly pick all 6 numbers. So there's 6 winning numbers. The only way to do that is to choose 6 from the group of 6. And so and that's going to be a 1. So it's basically 1 out of 40 C6. One way to win the $1 million prize. Here in the $1,000 prize, we have to pick 5 from the group of 6 winners. So it's 5C6. And then we can pick 1 from the group of losers. And so that's going to be 34C1, because we can pick 1 from that group. And then similarly down here, we need 4 from the group of winners. And this, sorry, this is a typo here. That's 6C5, not 5C6. And here we need to choose 4 from the winning 6, because we need to match 4 of the balls. And then we can choose 2 from the 34 losers. And these expressions here will give us the probabilities. Now for this problem, you're going to have to do this on your calculator. I'm just going to go ahead and take a break here and write them in. Oh, and then for the probability here, actually what we should do is not find the probability directly here. We know from the complement principle that if I don't, the only way to win 0 is to not win anything. And so you can think about this as 1 minus that stuff up there. Add those together. But in the end of the day, it's actually not going to matter, because when we multiply to get expected value, it's just going to be 0 times whatever this number is. So I'm not even going to bother calculating that number. But if you needed it, it would just be 1 minus the numbers above, because remember, the sum of these probabilities needs to equal 1. Okay, well, when you actually compute these on a calculator, this is a lottery, so it shouldn't surprise you that these numbers are going to be extremely small. So 6C6 over 40C6 turns out to be points and then 6 zeros with a 2-6 after it, and that's still just an approximation. So, but we'll get the idea there. And then this for 6C5 times 34C1 over 40C6, that's point, and then 4 zeros and a 5-3. Definitely, more likely than the top one. And then the $100 prize is 0.0022. And then to get the expected contribution to expected value, what we're trying to do is find the expected value of this column, the payoffs. And then, so we just multiply payoff times probability here. And when you do that on your calculator, you get approximately 26 cents. So the $1 million times this tiny small fraction contributes 26 cents of expected value. The $1,000 prize here contributes actually 0.053 cents, so a much smaller piece. And then the $100 prize, because it happens a fair amount, $100 times this probability is 0.22 cents. And then here, 0 times with the probability we didn't bother calculating is just 0. So we don't need to worry about that. I go ahead and add these guys up, and I get the expected value of this ticket, or this payoff. It would be 53 cents. So if I played this lottery over and over and over and over and over and over lots of times, the long-term expected value would be to get back 53 cents for each ticket that I play. Now, notice how the only possible outcomes are 0, 100, 1,000, and 1,000,000. And it's very weighted towards 0 because these probabilities of payoffs are extremely low. And then the last question here is, well, if $1 per ticket is charged, how much per ticket would the state expect to keep as profit? Well, so how would this work? The state would collect $1 from every person, and they would pay out, on average, this is the key thing, right? It's an uncertain amount that they pay out, but on average, they'd pay out per ticket this 53 cents that we found here. 53 cents. So we're just going to subtract that. And on average, the state would actually make 47 cents of profit per ticket here, and all we've done is expect. And here we didn't have to do an expected value for the collection because it was $1 for everybody. So it was like a $1 collection times 100% for each person. I suppose you could have some sort of payment scheme that was had some uncertainty in it as well, but in this case it's not. It's just a fixed dollar. Subtract our 53 cents, and hopefully the state would do this enough times though. I mean, they could get pretty unlucky and have to pay out a bunch of jackpots and whatever, and that would cause them to drop below this average for a while. But if they offered this lottery long enough, which is why states offer lotteries like this, every week, every day, so that on average they can go ahead and make that profit and use that to fund various programs.